So the numerical integration is useful for engineering applications uh, in many situations, and particularly in those situations when we have a formula or when we have a function for which there is no easy solution for the analytical approach, or there is simply no solution by the analytical methods. So in those situations, the numerical integration approach can be used. Or also in those situations when we just don't have any uh, function itself, we just have some data. So using that data, we can also perform the numerical integration. So in that situation, numerical integration is the only approach. So as with all methods for the all numerical methods, numerical integration is also not an exact method. It is an approximate method, and when it is an approximate method, there is an error involved in that method as well. Okay, so with this brief introduction, let's start the topic. So can you hear me well, and can you see the screen? Just
Yes.
confirm. Okay. So this is the chapter 1 of the textbook. Okay, before starting the chapter 1 of the textbook, let's have a let me show you a brief overview of what we have done in this course so far. I have prepared a table, and then uh, in this table you can see that what are the topics we have studied up to now, and what are the topics which we are going to study later on, and for which topic what type of uh, assessment we have been given. So for example, we have up to now studied 13 topics. So there are two topics left, 14 and 15. 14th is the topic today, and the 15 will be the in the next week. So we'll try to finish this topic, Newton-Cotes integration formula, in this week, and then in the next week we will be looking at the Runge-Kutta methods. So overall we have 4 weeks left, so we have plenty of time to finish these two topics. Okay, so in this table I have, this is the topic number, chapter title, and you can see that we have up to now 2 quizzes. Okay, but later on there will be quiz number 3 and 4. uh, yeah, quiz number 3 and 4 as well. So quiz number 3 will be on this Friday. Okay, quiz number 3 will be on this Friday, and then this will be from chapter 13 and 15. And there will be quiz number 4, then that will be in the next week on Friday, chapter number 17 and 18. Okay, so for these quizzes, you can look at those chapters. Okay, chapter 13 and chapter 15, the topics, and there are some practice quizzes as well, okay, which have been here. So for example, for the constraint optimization, there is this practice quiz number 10. For one-dimensional unconstrained optimization, there is practice quiz number 9. So if you look at this table, then we already have quiz number 1 and 2. These quizzes were about from chapter number 3 and 4. Quiz number 2 was from chapter number 5 and 6. The from chapter number 7 up to chapter number 11, we covered it in the midterm exam. Okay, and in the midterm exam, we also covered some other topics like numerical questions from the open methods and LU decomposition. In the assignments, we covered the numerical questions from the approximation and round off errors, truncation errors, bracketing methods. And in the lab assignments, we covered these topics. So up to now, we have only 2 assignments. I think we are lagging behind in the assignments. So I think very soon in this week, I will give you one more assignment and one more lab assignment as well. Okay, so this is a brief overview of the topics which we have covered up to now. So today's topic is Newton-Cotes integration formulas. Do you have any questions?
Yes, how many labs and assignments are left till the end?
Yeah, so initially I planned to give you up to 5 labs and 5 assignments. So we may have maybe 4 each, four quizzes, 4 assignments and 4 lab assignments. So there will be 2 more assignments and 2 more lab assignments.
Okay. Thank you.
Yeah, so we will have more. Yeah. Okay, and yeah, then this is the okay, the topic today. So topic today basically have 2 main methods, and these 2 main methods are the trapezoidal rule and the Simpson's rule. Are you familiar somehow by the trapezoidal rule and the Simpson's rule?
Yes, I remember something from calculus.
Oh, calculus. Okay. Yeah.
If I'm
So
not mistaken, but I remember.
yeah. Okay. So these are very common rules. So from somehow maybe you may have gone through these rules for the calculation of the integration. But anyway, we are going to do it here, and maybe we can have something new for you. For those, of course, those who have not gone through these rules, so this will be new for them as well. So these rules are categorized under the name as Newton-Cotes integration formulas. They are the most common numerical integration schemes. So they are based on the strategy of replacing a complicated function or tabulated data with an approximating function that is easy to integrate. And that approximating function will be a polynomial. Okay, so the main observation for the application of these rules is that since we know that for the polynomial functions such as a naught plus a1x plus a1x cubes, etc., we can very easily integrate these functions. So since we can very easily integrate these functions, therefore it is easy to find their value of the integration. So if somehow we can convert a complicated function into to represent it with the polynomial function, then we can approximate the results. So therefore, if we see that over here, the integration of f of x dx from a limit of a to b is approximately equal to fn of x dx. So where f of x is any is function in any form, like it is an exponential or a trigonometric function or whatever form, it is a complex function. Whereas fn of x is a function in its polynomial form. Okay, so in its polynomial form. So, but we are not using the equality sign over here. We are using the approximately equal sign over here. So this means that approximately equal, because we are making an approximation of this integral with the with another integral involving the polynomial function. So the polynomial function is in this form, which you all know, a naught plus a1x and plus so on. So therefore, the strategy is to represent this and represent that function with an approximating function, approximating polynomial function. Okay, so that approximating polynomial function can be of any order. Okay, most likely we start from the first order polynomial function, which is a line. Okay, and then we also try it with the second or third or fourth or fifth order polynomial functions to make them more detailed and more accurate as possible. So we start from the first order polynomial functions. Okay, so how we can represent it in a graphical format. So this blue line over here is the actual function. So we want to integrate it from point A to point B. Okay, so for the integration of point A to point B, our calculus course says that all the area under this curve from point A to point B is the value of the integration. Okay. However, when we approximate it with this straight line from point A to point B, so then we get this shaded area. Okay. Then we get this shaded area. So this shaded area we will get by this approach. So but here you can very clearly see that this shaded area is smaller than the actual value of the integration. So of course, this we already recognize that the straight line method is a as an approximate method. Okay, so approximate method. So this is the error. So the empty space over here is the error in this method. But of course, we can minimize this error. This is one of the purpose. This is one of the main objective in the numerical integration. We try to do it in such a way that we can try to minimize the error. So that we will see later. So this is the straight line approximation. In a parabolic approximation, we can take 3 points, including the points A and B, and then we can take another middle point, which is normally equidistant from A and B. So if we join these 3 points with a curve, okay, which is a second degree curve, so then we get a better approximation. As you can see very clearly, see that the approximation of the area under this curve is much better in the parabolic case than in the straight line case. So, but still in the parabolic approximation, there is some error which is presented in this part of the area. And then of course, there is an error in this part of the area. So, but the error seems to be much less in the parabolic approximation. Okay, so we can apply the straight line approximation, we can apply the parabolic approximation, and accordingly we will have the trapezoidal rule and the Simpson's rule. In the trapezoidal rule, we will apply the straight line approximation. In the Simpson's rule, we apply the parabolic approximation. So the approximation of an integral by the area under these three straight line segments. So now if we consider this same straight line approximation, but instead of just one area, we subdivide it into three areas like this. Okay, so here you can see that now by subdividing it into under three areas, we can see that the error has reduced quite appreciably. Okay, because now these straight lines are following much closer to the original curve. Okay, are following much closer to the original curve. So the errors have been reduced quite a lot compared with this previous case. Okay, so which means that by taking more number of areas, or by taking smaller intervals, we can improve the approximation. Okay, so with this we can look at the trapezoidal rule. Okay, so the trapezoidal rule is the first of the Newton-Cotes closed integration formulas. So we remember that we are looking at the closed integration formulas. There are also other formulas which are called as the open integration formulas. Just like in the roots finding topic, we have the bracketing methods and the open methods. Here we also have the closed methods and the open methods. But in this class, we will be only considering in detail about the closed integration formulas, as these are the formulas which have the most applications in the engineering practice. Okay, so Newton's trapezoidal rule is the first of the Newton's costs integration formulas, which corresponds to the case where the polynomial is the first order. So this is by definition. So for example, if the integration of this f of x dx from a to b, we want to represent it numerically, so we will approximate it in this case with the first order polynomial. So f1 of x is a first order polynomial. So now if it is a first order polynomial, its equation can be the equation of a straight line. Okay, its equation can be the equation of a straight line, and then when we input that equation of the straight line over here, that equation of the straight line can be integrated analytically, and we will do some algebraic manipulations. Okay, and then finally we will get this simple formula. So that value of the integral will be equal to b minus a times f of a plus f of b divided by 2. So b minus a into f of a plus f of b divided by 2. Geometrically, this is the area of a trapezoid. This is the area of a trapezoid. So for example, if uh, f of a and f of b are the two parallel sides of the trapezoid, we can take the average of the two parallel sides and multiply by them the distance between the triangles. Then we can multiply by the distance between these two parallel sides. Then that is the area of the trapezoid. So here we can see like this. So this shaded area is the trapezoid. So basically in the trapezoidal rule, we are finding the area of the trapezoid. As you can see, very clearly see that there is a lot of error in this case over here. So that's why we can apply it in a multi-step approach to reduce the error. So this area of the trapezoid we can find very easily by taking the average of these two sides, that is this vertical side and this vertical side. Okay, we can take the average and then multiply by the distance between these two sides, b minus a. So, and that is the area of the trapezoid. So if we remember this figure, then you can very easily find the area of the trapezoid and find the integral by the trapezoidal rule. Okay, so this area of the trapezoid, of course, has some error. For those situations where we don't know what is the true value, we can only approximate the error. Okay, we can only approximate the error. And by from some algebra, which is the derivation of this formula is given in the textbook. We will not go into the derivation of this. We will not go into the derivation of this formula. The approximate error in the trapezoidal rule can be found by this formula. Okay, so when we apply the integral under a straight line segment to approximate the integral under a curve, such as in the trapezoidal rule, the error may be substantial. And then this error is given by this formula. ET, error, is equal to -1/12 f double prime, and then this is a symbol for the error, which lies somewhere between this error lies somewhere between in the interval from A to B. So in this case, we can see that the error in the calculation is dependent on the second derivative of the function. Okay, second derivative of the function at a value uh, of this symbol. Uh, okay, and you can, but if you look at this formula, then you can see that this formula has a second derivative over here. So if you see that we represent in the trapezoidal rule uh, the function by a straight line. So if we have our polynomial of first degree, that means if our function is of a first degree polynomial, then f double prime will be 0. Okay, first degree polynomial f, the second first derivative will be a constant, and the second derivative will be a 0. So that means for that means we can say that the trapezoidal rule, we can represent exactly the error will be 0 in a function where the function is a linear function. But of course, there will be an error if the function is higher than the linear function, because there will be the second derivative of that function, which will be not equal to 0. Anyway, this formula can be derived. The derivation of this formula is given in the book chapter, but we will not go into the derivation of this formula. So we can just use this formula. Okay, next is, let's look at the example. Okay, a single application of the trapezoidal rule. That means if we have a function, for example, if this function is there, this is a fifth order polynomial function. Can we approximate this fifth order polynomial function with the trapezoidal rule? Yes, of course, we can do it. And this fifth order polynomial function, we want to integrate it from 0 to 0.8. So that means if we plot this function from the value of x is equal to 0 to x is equal to 0.8, what will be the area under that curve? Okay, since in this case we are taking the example, so we have taken the example in such a way that we know the true value of the integral. Because this is a polynomial, we can integrate it. So for example, if we will integrate it, it will be 0.2x, then it will be 25x squared by 2 minus 200x cubed over 3 plus 675x power 4 over 4 minus 900 x power 5 over 5. So this is a polynomial, so we can very easily integrate it. And then if we input the limits, then we can get the answer, which will be 1.640533. So for 6 decimal places, this is the true answer. So we already know the true answer. So how we can approximate it with the trapezoidal rule? Okay, so for the trapezoidal rule, we have this formula. I is equal to b minus a, fa plus fb over 2. Okay, so where value of a is equal to 0, value of b is equal to 0.8. So we can calculate this function at 0. So for 0, of course, all these terms will be 0. Only term remaining will be 0.2. If we will put 0.8 over here, so the answer will be 0.23. 2 over here, so that we can calculate it. So now if we input these values fa, fb, b and a in this case, 0.2, 0.232 divided by 2 into 0.8, the approximate value for the integration over here will be 0.1728. So the actual value was 1.64. The approximate value is 0.1728, which is of course much different over here. So that means, of course, the error is about 1.46, and it's about like 89.5% of error. Of course, it is expected in this case because we are trying to approximate a fifth order polynomial with the first order polynomial. Of course, there will be an error, but this is just for the illustration purpose. Of course, for the actual solution, we will not, this type of error is not acceptable. So that means you can see that 89.5% of the error has been obtained. So 89.5% of the error we can get like it is, you can get it from, for example, 1.46 divided by 1.6045 into 100, that will be 89.5% error. So the reason for this large error is evident from this graph. So for example, this is the original function, okay, and this is the approximated function, okay, this is the approximated function. So this approximated function is much smaller than this original function. So there is a great amount of error over here. Okay, so that was it. Okay, this is just for the illustration purpose, but later on we can improve this situation as well. That we will see in the some of the next examples. So right now, up to now, we have calculated this value of the integral with the trapezoidal rule. What about the approximate error, estimate of the approximate error? So for the estimate of the approximate error, as you can see that this was the formula, okay? So in this formula, we need the second derivative of the function, second derivative of the function. So we can find the second derivative of this function. So, well, these two terms will go out, okay? So second derivative of this will be 200 times 2 is minus 400, okay? And then 3 times 7, 65 times 2, okay? So it will be like this. So here we can find the second derivative, okay? So the second derivative, you can find it. And now if we integrate this second derivative from 0 to 0.8, okay, and then we can divide it by the its average, divided by b minus a. Then we can input this value f prime double prime of x is equal to this. Okay, so why are we taking the average? Okay, in the formula over here, what we have seen over here is that we are finding the second derivative at some value of which is represented by this symbol, okay, which is represented by this symbol, and where this symbol lies somewhere in the interval from a to b. So we are, it's assuming that this is between this is an average value, okay. We can say that this is an average value of the second derivative, okay, between b and a. We assume, okay, we assume that this is an average value. So in this way we can approximate this error, okay. So because it is it lies somewhere between interval a and b, so as an arbitrary rule we can take that it is an average value of this between b and a. So we are taking actually the average value of the second derivative, okay. So the formula for the average value is equal to in the integration terms, it is given by this. It is given by this, so it is b minus a. Okay, so the this comes out to be minus 60. So now if we will input this minus 60 into this equation, that is the value of this f double prime. We put input minus 60, and then it is minus 1 over 12 and b minus a cube. So here we can see that the approximate error in this case will be equal to 2.56. Approximate error is 2.56. Here, but actually the what was the true error? True error was 1.46. Of course, it is not that uh, close to that true error. Even the approximate error estimate is not that accurate. But what we can see that it is actually of the same order of the magnitude. Okay, it is not like 10 times different than that. Of course, this can be improved. So a discrepancy does exist, however, because of the fact that for an interval of this size, the average second derivative is not necessarily an accurate approximation of f double prime of psi. So thus we denote that the error is approximate by using this notation rather than exact by using ET. Okay. So that was example 2.1, 21.1. So in order to improve the situation, uh, instead of a single application of the trapezoidal rule, we can have the multiple application of the trapezoidal rule. That means we can reduce the intervals from, you can taking a single large interval equal to b minus a. We can divide that b minus a interval into n segments. Okay, n segments. So n can be any number greater than or equal to 1. Okay, so for example, we can divide it by 2 segments, 3 segments, 4 segments, etc. So in that case, then the width of the interval will become h, which will be equal to b minus a over n. And we will have then n intervals. So first interval will be from x0 to x1. Second interval will be x1 to x2, where x0 is equal to a. x1 will be equal to a plus h. x2 will be equal to a plus 2h. x3 will be equal to a plus 3h, etc. And then for each integral, we can approximate it with the linear, the equation of the line. And then we will integrate it. And then after the integration, we can simplify it. Okay, we can simplify it. And after the simplification, the formula will become like this, as it is given over here. As it is given over here. So the simplified formula in this case will be like this. So for example, if here in this formula, we can take the values of h as common, and here you can see that we can take h by 2 as common over here in this formula, and then we can see that fx naught will appear 1 time, but whereas fx1 that will be appearing 2 times, fx2 that will be appearing 2 times. So all the middle terms will be appearing 2 times, and then there will be one single term at the end. Okay, so this will give the formula for the multiple application of the trapezoidal rule. So here we can represent it in the graphical format, the multiple application of the trapezoidal rule. So there is, of course, an error of the multiple application of the trapezoidal rule as well. This error of the application of the trapezoidal rule can be represented by this formula: 12 b minus a cube over 12 n square into the average value of the second derivative. So f bar double prime, this is the average value of the second derivative. This, of course, this formula can be derived. The derivation is, of course, is given. We are not going into the derivation of this formula. But if we compare this with the previous case, we can see that in the single application, there was n was equal to 1. Okay. But here in the multiple application, n is equal to greater than or equal to 1. So here you can see that more will be the value of the n, more will be the number of segments. and less and less there will be the error. Okay, if we take the, because n is now appearing in the denominator, so higher will be the denominator, lower will be the value of this fraction. So thus, if the number of fragments is doubled, the truncation error will be quartered because it is the square of n. Okay, so in this case, we can see that taking more number of the segments will reduce the approximate error. So here we can apply it with the help of this multiple application trapezoidal rule. So it is the same equation as before. This is the fifth order equation. And then this fifth order, for this fifth order equation, instead of now, if we take just one single application, we can take two values over here. Okay. If we take now two values over here, then we can apply this formula. Okay. So 0.8 is b minus a, and then 0.2 is the value at the first point. 0.232 is the value at the last point, and the value at the middle point at 0.4 is 2.456. Okay, if we can calculate this value at 0.4, if we put 0.4 over here, so the value is at the middle point. So the middle point is multiplied by 2. First and the last points are represented like this. And then by the formula, it is to be divided by 2. Okay. Divided by 4, sorry. So which is actually 2 times the n. Okay, it is 2 times the n. 4 is equal to 2 times the n. Okay, so it will be 2n. So in this case, then the error will be 0. The value which we got is 1.065. The true value was 1.64, and the error will be 0.57153. And the now the error has been reduced from 89% to 34.9%. So you can see that by increasing the from the value of n from 1 to 2, the error has decreased from 89% to 39%, 35%, 90 to 35. So that means a reduction of about 4 times. So in this case, the percentage of error is the true percentage of error. The approximate error is by the formula is 0.64. Earlier it was more than 2.6. Okay, so it is 0.64. The value earlier was 2.56. Yes, now it is only 0.64. So that means now the approximate error has also reduced. So we can we can also check it with the various values of n. If we increase the value of from n is equal to 2 to 3, the value of the integral will be 1.3695. Okay, if we will input these values. Okay, so let's see it. Let's try it by the maybe in Excel. Let me put this in here. So I have this, so let's try it n is equal to 2, okay? So we need to, for this trapezoidal rule, okay? So first we need to find what is A. A is 0, B is 0.8, and now we are taking n is equal to 3, okay? So when n is equal to 3, then h will be equal to, that h will be equal to b minus a divided by n. So h will be equal to 0.2667. Okay, so in this way, then we can calculate the values of the function. So x naught, so we need x naught. So because here we are now taking 3 segments over here, okay? So we need x naught, okay? We will need x1, x2, x3, okay? So what are these x naught? So x naught is equal to a, okay? And x1 is equal to, this x naught, x1 is equal to x naught plus h, okay? This one. And then similarly, x2 is equal to x1 plus h, and then x4 is equal to, so here we have calculated these values. And now we need to calculate the f of x values. F of x values. So f of x values are, what are the f of x values? So f of x values are is equal to the function 0.2 plus 25 times x minus 200 times x square plus 675 times x cube minus 900 times x power 4, and then plus 400 times x power 5. So this is how we represent fx. And now what I can do is I can just copy it down, and then here we have this values. So so for the trapezoidal rule, so the first value of the function will be the same, okay? That means if in this trapezoidal rule, let me show you the formula for the multiple application. The formula for the multiple application is this. This is the formula, okay? So you can see that in this formula, we have this value, okay? f of x naught. So this will be the, so that means here we are going to calculate the value for the function by the trapezoidal rule. So trapezoidal rule, okay? Trapezoidal values, okay? So this will be the first value will be the f of x naught, which is the same value. And the second value is, so you can see that the second value is, that is the middle values are multiplied by 2. The middle values are multiplied by 2. So therefore, I will take 2 times this middle value, and then I will copy it to this value, and the last value is not multiplied by 2. So last value is the same as this. So it is this. And now I can add them together. Add them together. So it will be 10.278. So the final answer will be this value multiplied by b minus a over 2n. Okay, so the value of the integral will be equal to this value multiplied by b minus a. B is this, minus a is this, and then divided by 2 times the n. N is this. So this is the this is the value 1.3695. So this is which is the same which we got, which is the same value which we got over here. So similarly, we can calculate the value for n is equal to 4, which will come out to be like 1.4848. Okay. So let's do it for this as well. Okay, so here I think what I need is one more value, x4, and here I need is value as n is equal to 4. So h is this, and this will be equal to this value plus h. So it is this, and now yeah, it is here, and we can calculate it here. Now this value will be the same, this will be multiplied by 2, all these values will be multiplied by 2, and then the last value will be the same, and now I can add equal to sum of these values, and it is 14.484. So this value is equal to this multiplied by b minus a divided by 2 times n, which is this. So it is 1.4848. So it is 1.4848. So similarly, you can add or calculate all these other values. Okay. So is it clear how we are going to perform these calculations on Excel?
Yes.
Okay. So in this way, then what we can do is you can complete this table. In fact, we can even write a short program in MATLAB as well, which can immediately provide these values. So that I will illustrate to you tomorrow in the lab class. Okay, so this that was the trapezoidal rule. Next, we will look at the Simpson's rule. Okay, so we'll look at the Simpson's rule in our next lecture on Wednesday. So that's all for today. So do you have any